All right, everybody, good day. So we are starting a new unit today, and it's kind of like a separate beast. Everything up until this point has been like polynomial this, maybe some roots thrown in there, like square roots, but x to the thirds, x to the sixth, and solving equations and their graphs and all that stuff. Today we're going to talk about a separate classification of functions that are called exponential functions, and we're going to get an intuitive feel for them first with our warm-up right here. So number one, would you rather have $1 million right now? Or would you rather we give you a penny and then it double every day for a month? Well, every time it doubles, what do you multiply it by? 2. Makes sense, right? Yeah, multiply by 2 every time. How many days are in a month? We kind of collectively agreed that would be 30 days in a month. All right, so how many 2s you got to multiply by then? 30 of them, right? So get out your calculator, very much a calculator thing right here. Can't do this in your mind. I mean, you could try, but really hard. Could have $1 million. I'll write down that as a comparison. $1 million or 1 penny times 2, 30 times. Now, as you should know by now, if you multiply by something over and over and over again, that's just raised it to bigger and bigger power. So if I multiply by 2 30 times, that'd be 2 to the 30th. So get your calculator out and type in 0.01, 1 penny, times 2 to the 30th, doubling it 30 times, and you get a big number. And if you're careful with your commas and stuff like that, it turns out to be about $10 million right there. So that is to illustrate the power of exponential growth. If something keeps doubling and doubling and doubling and doubling and doubling, it grows really, really, really fast. In fact, that's one of the fastest things that grows in the universe. So that's an example of an exponential. When the exponent gets bigger, 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 after 30 days or after 31 days or 32 days or however many, it just gets bigger and bigger and bigger right there. So that's one thing you're going to find about exponential functions. They grow really fast. They're cool like that. All right, that's it for number one. Number two, when you multiply a number by something more than 1, does it get bigger or smaller? That's the big question. I hope you know if you multiply by something more than 1, the numbers get bigger, right? Okay, so write that down. When I multiply by something more than 1, it gets bigger. We're going to need that today. Today we're just multiplying by 2 over and over again, and then the amount of money just got bigger and bigger and bigger. However, if you multiply by something less than 1, like a fraction, like a third or a fifth, over and over and over again, every time you multiply by a fraction, things get smaller. So if you multiply by something less than 1 over and over and over again, your numbers get smaller. Very important right there. There's our basics. And that was it. That was all we got to do for our warm-up right there, is just talk about intuitively what happens when you multiply by something more than 1 or less than 1, and kind of a concrete example with the penny thing. So there we go. Here's your LGs. It's short and sweet today. Because we took an extra day for the ACT and we're still catching up from snow days, today will be the last day where we are kind of off schedule. Starting next week, we'll be back on schedule. Unfortunately, that means we are going to skip the work day. So you will not have a work day on Monday over this. We'll have another lesson and proceed from there. So your job is to get the homework done this weekend all on your own. You can do it online. You can do it on paper. Either one is a valid option. The questions do match up. And your homework is going to be Unit 7. So your first homework will be called Homework 7.1. And it'll be these problems right here. 1 through 13 odd and 17 through 31 odd on page 361. They're pretty straightforward once you get the basics down. It's about graphing, so we're going to start talking about the graphs of exponentials today and what an exponential even is and all the basics. Once we got that, we'll be off and running. Monday, we'll come back and start talking about how to solve problems involving them, but one thing at a time. Homework 7.1 due Monday, not going to have a work day to get that taken care of. All right, notes, 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 new unit, new heading for your notes. This is Unit 7, exponential functions. Here we go, exponential functions. This will follow us for the next couple units. This unit will be about exponential functions. The next unit will be about their inverse, called a logarithm, which we'll learn, and of course it will reference this one quite a bit. So Unit 7 and Unit 8 will be lumped together into one test when we get done with both of them. Well, let's dive right in. Here we go. Section 7.1 is about graphing exponential functions specifically. And let's get our basics down. Here we go. What's an exponential function? Well, you should probably define what it is first. An exponential function, something that looks like this line right here in the middle, f of x equals b to the x. Okay, so if you don't, write that down. Write that down. We'll try that in all our basics. B to the x. This is a different beast. The base will be a number, and the exponent will be a variable. That's why it's called an exponential, because your variable will be in the exponent. So a graph of 2 to the x, or 7 to the x, or 5 to the x, something like that, that is what an exponential is going to look like. Down below, based on that, is what all the basics are going to be for anything that has exponential growth. This is a graph where it gets bigger and bigger and bigger, just like our warm-up did with the penny. It just got bigger and bigger and bigger. You keep doubling it and doubling it and doubling it. It just keeps growing and growing and growing. Over on the right, you see that little graph. And you also see up to the side what it's defined as. F of x is b to the x. But this is only the graph when the b is more than 1. If the base is more than 1, then like we just talked about in the warm-up, if you multiply by something more than 1 over and over and over again, the numbers just get bigger and bigger and bigger. So this is what you would expect the graph to look like if the number on the base is more than 1. 1.01 to the x would look like this. 2 to the x, 7 to the x, anything like that. Of course, with any new graph and any new parent function, it's very important to get the domains and ranges and all the basics of it figured out. So over there on the left is the domain. These graphs exist everywhere from the left to the right, from negative infinity to infinity. You will never need to take anything out of these domains because the same 2 rules apply that I've always been harping on. You only need to worry about even roots and dividing by 0. This equation has no roots and has no division either, so you will not have to worry about roots anymore. You're out of the woods on that. Yeah. The range, that is 0 with a parenthesis to infinity, and I'll talk about why that is in just a second. Also important to know, a key point on this graph is 0, 1. Crosses the y-axis at 1. So there's the y-intercept by default. Also, this HA thing, we need to talk about that. That stands for a horizontal asymptote. Asymptote. We'll have to define all these terms. And of course, you got some end behavior stuff there as well. Limit as x goes to negative infinity goes to 0, and limit as x goes to infinity goes to infinity right there. But I don't want to just throw some things at you and just, write them down and hopefully you understand them. Let's actually take a minute and play with the concept to see why these are the domains and the ranges of all this stuff. So let's see if we can do that right now. Okay, well, let's build it up. Let's do a quick example of, say, 2 to the x. That's a good one. It just doubles. It's simple. Doubles, doubles, doubles. Remember what this means is I'm multiplying by 2 over and over and over again. How many times? X times. I don't know how much x is. That's what we're good. One thing you should know is that anything raised to the 0 power is, anybody know? Anything raised to the 0 power? It's 1, right. So that's why for any exponential, if you plug in 0 for x, you will always get out 1, because who cares what the base is when you raise it to 0, it's 1. Which is why this will always be, by default, your y-intercept. 0, 1. When you plug in 0, you get out 1. Of course, you could stretch things later on, right? Maybe it could be twice as high or 5 times as high. So there will be stretches and shifts, the normal kind of nonsense like that. And every time you go over 1, you basically, well, what's 2 to the first? It's 2, right? So now I'm up here at 2. Then when you get to 2, oh, now it's 2 squared. Well, that's 4, isn't it? And if you get to 3, well, darn, that's way up here at 8. And you can see what the graph is doing. Every time you do this, it just goes bigger and bigger and bigger. So kind of connecting the dots in here, there aren't really any dots. It's not like the dots are a false thing. They're just kind of some test points. But it looks something like this. Now let's try to generalize this and go backwards. If every time you go to the right, it multiplies by 2, then going the other way, if you go to the left, you're dividing by 2. So if I'm here, it's 8, I go over 1, I'm dividing by 2. And if I go over by 1 again, I've divided by another 2, and divided by another 2. Well, extending this pattern, if this was 1, then 1 more over would be down to a half right there. And if I go 1 more over than that, I got a half of a half, which is a fourth. And if I keep having things and having them forever, if you have something and you keep having it, the pieces will get very, very tiny, won't they? But they won't ever go away. No matter how much you do this, there'll still be some little left over, and I can still always cut it down into another half, another half. I'll never have nothing left, which means on this side, it levels off to this axis, but it doesn't actually ever touch it. And that's a very important thing right there. It never touches it. Hence why the domain and the range is the thing you just wrote down. This is defined everywhere, but the range, it starts at 0, but it doesn't actually touch 0, does it? It gets really, really close, but it doesn't actually get there. So it goes from 0 up to infinity, but we have to put a parenthesis on the 0 because it doesn't actually get there right there. So that's why all those things are there from your thing. Your y-intercept is at 1. That's what your domain and your range is. As far as end behavior goes, looking at it now, again, this just means a fancy word for what happens as I go to the left, right? As x goes to negative infinity, well, if you look on the graph, as you go really far to the left, it doesn't blow up to infinity. It doesn't go down to negative infinity like the old ones do. What's it do? It levels off to what number? 0. So this time on this end, the end behavior is 0. It approaches 0 as you go to the left. As you go to the right, well, that's a little different. As you go to the right, it just gets bigger and bigger and bigger, right? I'm going to the right, it just gets bigger and bigger and bigger. This one goes all the way up to infinity right there. And I think this is the first time we've actually encountered this term, so I better darn well define it. An asymptote. Let's define an asymptote, because we haven't really encountered that too much yet. An asymptote is a line that your function approaches but never actually touches. That's a big term right there. We'll be talking about that a lot in the future. Asymptote. Line that your function approaches but never actually touches. And there is, yeah, sure. And there is a line right here. This little blue dash line I just drew here, that's a line, and it approaches, it doesn't on this side. Gets really close. Does it ever touch it? No. Gets really, really close. So now this is a horizontal line, right? So this one would be called a horizontal asymptote. And lines have equations. This would be the equation y equals 0 right there. So those are the key things you're going to have to think about for every single exponential graph you see. What's the domain? What's the range? What happens on the ends? Where's it level off to? Levels off to y equals 0. Of course, if we add a +2 on the end of our graph, what would that do to everything? It'd move it up 2, right? And so the asymptote wouldn't be at 0, it'd be up at 2 and things like that. So we're going to have some stretches and some shifts to deal with this stuff. But those are your basics right there. Any questions over the basics? Anything at all? All right. So that's kind of what that all is about. And that summarizes that slide right there. Let's take a look at a graph. Graph 2 to the x. Well, we kind of just did that. Doubles every time. You're welcome to make a table if you want. I don't think you really need to. You should know that the base here, 2, is more than 1, right? So it will grow. That's what exponential growth is. It gets bigger and bigger and bigger. And if you want to make a table, be my guest. But you should be able to tell me just by looking at this thing what the domain and range is. The domain would be negative infinity to infinity, right? The range would be 0 to infinity with parentheses. The intercept is at 1. The asymptote, there is an asymptote here, y equals 0. And as you go to the left, this thing approaches 0. And as you go to the right, this thing approaches infinity right there. Let's try a more complicated one. Okay, so jot this one down. Like usual, the parent function will be pretty straightforward. Here's your rules. Here's how an exponential looks. And then they're going to jack with you and put stretches and negative halves in there and flips and all kinds of stuff. But like any other function, we're going to analyze it the exact same way. In fact, I'm not going to give you notes over it this time. We'll just think it through very logically. Okay. So let's think about what this might look like. Let's see. First off, what are we comparing this to? A basic exponential looks something like just a number to the x, just a number to the x. That's all we're talking about so far, right? Okay. Well, let's see. What is different between this one and that one? Well, first off, can you tell me where the exponential is? I think that's the exponential. Would you concur right here? Yeah, that's the thing with the base and the exponent. So that is my function. Now, by now, we should know what happens when we take our function and multiply it by something. It's a vertical stretch, right? Now, a vertical stretch by a half, that means it's only half as big. So it's going to actually get kind of half as tall. But more importantly, what's in front of this? I see a negative sign. And you should know what happens to any function when I put a negative sign in front of it. It vertically reflects it, right? So right off the bat, I'm going to think that this negative sign takes this graph and kind of makes it look more like, oh, I don't know, something like that. Would you agree kind of flipping it over that way would be vertical? Cool. And then what's the +1 do to a graph? We all know what that does. Moves things up 1, right? So where did this level off before? There was a horizontal asymptote at 0 by default, right? But the +1 takes the whole thing and scoots it up 1. So a rough sketch of this thing is, it's not going to level off at 0. It's going to level off at 1. Please label asymptotes as an equation, okay? Don't write 1. It has to be y equals. It's a line. It might not, you're not going to really see it if you graph the thing. It's not going to show you this line. You have to know it's there. That's why it's a dash thing. But it looks something like that. And we just said it kind of opened down, right? So it's going to level off on this side. It's going to kind of go down something like that-ish right there. If you want more specific points, of course, you're welcome to plug in different x's and things like that and all that. There's one other little subtle change I didn't really consider too much. It's not x, it's x plus 4. What happens when you replace your x's with stuff? That's horizontal junk, right? So this would also be shifted which way? Well, not 4 to the right, but 4 to the left. So I'd take this picture and kind of scoot it over a little bit too, something like that. But you kind of get the gist, right? The negative flipped it right, the 1 moved it up. That's the main point. You can get your calculator out, and really, if you want to get down to the nitty-gritty of where exactly everything is, that's fine. But like most graphing things, your job is to get the basic idea down, give me a rough sketch. I'm not going to sit there with a microscope picking on you for various points that are a little bit off or something like that. Here's another example. Let's take a look at this one, example number 3. A little slightly different beast. Identify the value of k and write a value for this graph of this function as it relates to this parent function 3.5 to the x. Now, let's just think about what 3.5 to the x looks like. That's a base more than 1, right? There's no other things on it, right? There's no pluses or minuses. So by default, I'm going to think it looks like our normal thing right there. Well, look at the graph you have. Does it look exactly like this? What's different between what you have and what you know? That one is shifted down 2, would you probably agree? Yeah. Doesn't level off at 0, levels off and down at -2. So how do you move something down 2? Yeah, well, you add not 2, -2, yep, and that moves it down here. So if I took this original function and added -2, then I would get that right there. Does that make sense? So the answer to this question is k must be -2. If I took this original thing and plugged it in, what would I have to add to it to get this darn thing out that they want, which would be -2. So those are pretty easy if you know what they're asking for, right? A couple problems, you're just looking for it and see where it shifted up and down, right? And whatever that is, that's kind of the number on the end that they want you to write down for that. Okay, now this is a quickie. Determine whether each function represents exponential growth or decay. Now, if multiply by something more than 1 makes it grow, multiply by something less than 1 over and over again makes it decay. We're going to talk about that more specifically in a second. But really, you just look at the bases, okay? Part A, the base is 5. Would you agree? That's more than 1. So what's this graph going to do? This one's going to have exponential growth. This one, the base, oh, that's a fraction. It's less than 1, isn't it? So what's that going to do? That's not going to grow. That's going to decay right there. This one here, 4/3. Anybody know if that's more than 1 or less than 1? More than 1, so it's going to grow, right? 1.05, is it more than 1? Barely, but it counts, doesn't it? So that would grow very, very slowly, but it would still grow exponentially. And the last 1.85, that's less than 1, right? So that one's going to decay downwards. And those are the basics of what you need to know about that stuff. Any questions about that? Okay. Well, here's one where the base is less than 1. We haven't talked about that yet. Let's go ahead and write down this particular example. This is going to lead into the last topic of the day. There is a way to force this thing to have a base more than 1. So there's a way. There's a way. 1/2 to the x. Well, we haven't talked about the graphs formally yet of ones where the base is less than 1. This has all been about bases more than 1 so far, correct? How the heck am I going to get this base to be greater than 1? I got tricks. Check this out. Would you agree that a 2 to the first on the bottom is the same as a 2 to the negative first on top? Remember that? What's a negative exponent mean? It means it's on the bottom, right? So they're the same thing. I don't need to write this as over 1. Anybody know what you do with your exponents when you have something raised to a power and it's raised to another power? What do you do? Anybody know? You do multiply them. That's exactly right. -1 times x is negative x. So another way to think of this particular function, 1/2 to the x, in a roundabout way, that's the same as saying 2 to the negative x. What in the heck would that look like? Well, I know what 2 to the x looks like, right? 2 to the x looks like that. What happens when you replace your x's with negative x's? When you do x stuff, you do horizontal crap, right? And when there's a negative, what's that do? That's a horizontal reflection. So this graph will look exactly like this one, only horizontally flipped. And that means it's going to not, that was terrible. The asymptote. Very slowly level off. It's going to look something like that. The same kind of shape, horizontally flipped. So even if the base is less than 1, I can force it to have a base more than 1 with a negative exponent if you prefer to look at it like that. Or, better yet, probably just want to remember that when you have a fractional exponent in the first place, it doesn't grow, it decays, just like that. So let's talk about the decay part. That's the other half of this stuff today. I guess that was all they really, no, shoot. I'm supplementing that. That's not good enough. Okay, last part. When your base is between 0 and 1, meaning it's a fraction, when that happens, you will not have exponential growth. You will have exponential decay. And the whole thing is going to be flipped from what you just kind of saw, like we just did. So just like we just talked about, we just did a half example. And the half is less than 1. You don't need to go through all that convoluted logic and figure out, okay, that's 2 to the negative x. You don't need to do that. You need to know when your base is less than 1, it's going to go down instead of going up. Now, the main highlights are the same. It's still going to have a y-intercept at 1. The domain and the range will still be the same for the same logic. It does exist everywhere from the left to the right. It does still kind of level off right here at this asymptote. It does have another asymptote at y equals 0. There's this imaginary line. It's getting very, very close to, but not quite touching. The only real difference between these two is what happens on the ends. On this end, this time, for the one we just talked about, as you went to the left, it went to 0, correct? For this one, when you go to the left, it goes up to infinity. So your end behaviors are switched on this one. As you approach negative infinity, your graph blows up. It gets bigger and bigger and bigger. It goes all the way up to infinity. As you go to the right, well, the darn thing just levels off to 0 right there. That's the main things you need to know about exponential decay. In fact, it's the exact same thing as on this slide right here. Okay, take a look. Did I miss anything? I don't think I did. Same exact stuff. Goes down like that, levels off on the right. And again, just like anything else, I can have stretches and shifts and things based on this. So let's see if we can find one that's based off of that. We'll call it a day after that. Let's do this last one right here, then we'll be done. G of x is -2, 1/4. Common mistake some people will do, don't let this be you. Right off the bat, can you multiply the -2 and the 4th together? The answer is no, because of PEMDAS. This thing is raised to an exponent, right? So it's all by itself. It does not play nicely with this -2. You're always going to have this number in front. Do not put these together. You cannot do that. You have to do exponents before you do multiplication. So if there's a number in front, you're just kind of stuck with it. Well, right off the bat, guys, can you tell me what 1/4 to the x looks like? Forget all the other junk, just 1/4 to the x. Well, that'd be a base less than 1, right? So it'd be an exponential that's going down. Okay, so right off the bat, I'm thinking this is an exponential that goes down. But like anything else, let's look at the other changes. That's what 1/4 to the x would look like. But we don't have 1/4 to the x. We got this stuff. So let's start looking at what's different about it. Well, right off the bat, let's see. What's in front of it? A 2, right? What's a 2 do to something? It makes it 2 times bigger, right? Also, there's a negative in front of your function. In front of your function, that'd be a vertical reflection. Fair? Okay, so there's a vertical reflection. Also, it's not x up there, it's x minus 4. That's when you replace your x's, that's horizontal shifts, right? So move 4 to the right. And what's the 3 do? Of course, that moves it up 3. So kind of putting it all together. And again, I'm not going to like sit here and do point by point and figure out exactly like it looks, but putting kind of thing. Here's what 1/4 to the x would look like. Reflecting it would look more like this. Do you buy that? A vertical reflection. And then if you add the 3, what's that do? It just moves it up 3. So I'm thinking up here at 3, 1, 2, 3. That's probably where it's going to level off to. So my horizontal asymptote will be there. There it is. There's always an equation for that. Y equals. On your test, when I say horizontal asymptote, don't write 0. You have to write y equals, well, not in this case. It's not 0. What is it? It's not 0. 3. I'm just being stupid. Make sure you write y equals. Make sure you write y equals, or else I'll have to dock you half a point or something like that. But as we said, it's going to be vertically reflected. So it's going to open like this, and it will hug the asymptote. That's kind of your guide. Something like this. Of course, that's not perfect. It's a rough sketch, but that's kind of the point, right? I think as the farther in we get with this, we don't need to sit here and worry too much about all the little details. Just, are you watching for reflections? Are you getting the right shape? Is it in the general right spot? And that's essentially all there is to that. Questions over anything about exponential growth or decay? Okay, remember, it grows when the base is more than 1. It decays when the base is less than 1. And here's your default domains and ranges that will just require some shifts and stretches and things like that. And that concludes today's lesson. You got some time to work too. That's good. You got a good 15 minutes to get started on this. No work time on Monday. Come on Monday with it done and ready to work on actually solving some equations instead of just looking at graphs. That's it.